Welcome, everyone. And just to confirm, you have the right webinar. This is number 6 in our developer webinar series for Solaris 11. Bill Kanaki is going to cover writing Oracle Solaris 11 device drivers. I'm Mike Mulkey. I'm the manager of the Oracle Solaris Partner Adoption Team in our systems organization, and I'll let Bill introduce himself. But I do want to say that this webinar series is a direct result of the work our ISV engineering team is engaged in with our partners in moving their applications to Oracle Solaris 11. And Bill is a part of that team, and he's going to speak to it specifically with respect to hardware device drivers in Solaris 11. I do want to note, if you're on for marketing overview or a product overview, this is not that. This is a deep dive, hands-on, very technical presentation covering real deep, dive kind of feature, tool, functionality stuff around the optimization in the development process for Solaris 11. So I just want to make sure and level set you that you're in the right place. But I do think by holding through these, you'll be able to get a better understanding of some key Solaris features, especially around Solaris 11, as well as understand some of the key advances Solaris 11 has made over prior releases of Solaris. So hopefully you're comfortable with that and in the right place. If we take a look at the next slide before Bill starts, I just wanted to give you a real quick view of the webinar series itself and the subjects that we've identified as most beneficial to developers in moving to Solaris 11. As you can see, we've covered 5 topics already, and I just want to note those recordings and slides are posted on the webinar registration page, and I'll cover that again at the end of today's presentation. But the slides for today, if you by chance are on phone or coming in VoIP only, and you want a copy of the slides, they are up there today. And to get to the registration page, just Google Solaris 11 Developer Webinar, and this registration page will pop up, and you can download the slides right now. But as you can see, these webinars are continuing through the summer. We're going on continuing the biweekly basis, every other Tuesday, 9 a.m. Pacific. The one exception is we're going to skip 2 weeks over the 4th of July period for a summer break. But other than that, you can just bookmark this in your calendar. Every other Tuesday, 9 a.m. Pacific, these are going to continue. I do want to note we will have a poll at the end of today's presentation. That's what we were kind of working through. Hopefully it works. We do want to get your feedback on any future topics of interest. And finally, there is live chat. We've got Solaris 11 subject matter experts on the line during today's presentation to handle live chat. Please use their expertise for any questions you may have. I'm paying them handsomely, so they get to be here today. So let's make sure they have some work to do. So go after it on live chat. That's what they're there for. We're collecting those questions and do plan to post an FAQ on the registration page. So look forward to that. Okay, without further ado, I'm going to turn this over to Bill. He's got a fun fact for the day. It's time to get technical. So, Bill, it's all yours.
Okay, so fun fact for today. You may or may not know that there is a transit of Venus in front of our sun. This is a pretty rare event. The next one will occur on December 11th, 2117. Most of us probably won't be here for that. They happen twice, 8 years apart, about every 100 years or so. I caution you to pay real strict attention to safe viewing that is the sun, and you can damage your eyes. There is a URL provided here, transitofvenus.org. It's a good place to go to check out this important astronomical event for today. So let me talk about what I plan to do today. The goal is just to introduce you to device drivers and how drivers work in Solaris. I'll give you an example of a basic driver construction, so you should go away understanding at least the basic rudimentary aspects of building a device driver, and of course, pointers to documentation on how to get assistance. I also want to caution you that the kernel is a pretty dangerous place to write code. You're not protected as you are in user space. You can see and touch everything in the kernel, and bad things can happen if you touch them. You need to pay particular attention to details when writing your device driver and be rigorous about your debugging and testing your code. Drivers can often do really bad things. You can panic the system, hang it. You can destroy uninstalled operating system, and you can even break hardware in some cases, although that's pretty rare. So what we can talk about? Well, what are drivers? Major driver types, the devices and the device tree and how they're constructed, a little bit about the driver architecture and anatomy, how to compile and link your driver, how you install it, load and unload the driver, and some pointers on testing. What are drivers? Drivers simply implement a set of routines used by the kernel and by user programs to interact with hardware devices or imagined devices. They need not connect specifically with hardware. Some examples are things like RAM disks. Drivers can even take input from other drivers and export I/O above them. So you can have layered device drivers. I'm not going to specifically talk about that today, but that's something that drivers frequently do. One of the things that makes it different from writing a typical program is that there's no main segment. The kernel is the main segment. So what you're doing is you're simply linking in your routines for how you interact with your device. It lives in the kernel address space, and as such, it should only link to other kernel routines. Attempting to link outside the kernel can have bad effects, usually causes a panic on SPARC machines, although on x86 architecture it doesn't necessarily panic, but unpredictable behavior can occur. And of course, one of the things that we care about in Solaris is a robust and stable environment. Drivers, of course, must be reentrant, interruptible, and preemptible. That is, your device driver can be interrupted by another instance of your device driver. Major driver types. There are two major types of drivers, character and block. Character drivers present a sequential stream of bytes in and out. A block driver provides a buffer at a time at an addressable place in the device. So an example, character device drivers are things like serial ports. You read a character, you write a character, or you write 10 characters or read 10 characters. A block device is something like a disk drive, where you say, index this far into this file and give me this much data. A subset of character devices are streams devices. It uses a special API, the Stream.io package, and it's a special subset of character devices. Again, it's a sequential stream of bytes in and out. It's important to note that drivers can present both character and block mode aspects. So a little bit about devices. So let me talk for a second about what happens when you power on your system. The CPU gets initialized, and then the system attempts to run the firmware. Some power on self-test usually, and then a boot environment. In the SPARC world, that's open boot. On x86 systems, that's the BIOS. One of the things that happens at this time is the firmware attempts to identify each device that's visible to the system and build a device tree. It doesn't necessarily identify all devices, only those that the BIOS or the open boot know about, and usually self-identifying. It obviously must identify any devices that might be needed during boot. So then the operating system boots, in this case Solaris boots, and reads the device tree provided by the firmware. Now, again, not all the devices have been identified, but then Solaris attempts to descend that tree of devices and associating a device driver with each device, starting at the root node, traversing down each branch until it reaches a leaf node. Since not all devices are identified, Solaris also attempts to probe the fabric of devices and look for other additional devices. Solaris can add and remove devices at any time while the operating system is running. So if you have a hot plug event, a device can be discovered and the device attached and loaded at that time. Here's an example of the device tree. There are user commands to examine the device tree. PRTconf is a way that you can display the device tree and all the information that the system knows about that particular instance of the device. There's also a file system, /devices, that represents the device tree. And if you go to /dev, you'll notice that it's a link to those specific devices. There's also a programmatic interface to the device tree, live GetInfo. Devices are identified in a number of different ways. So in the case of PCI or PCIX or PCI Express devices, they're self-identifying. That is, the device itself expresses its vendor ID and product ID, which is in its config space in its firmware. And the firmware or Solaris can read that and identify that device. There's an association between those device compatible properties or device IDs and a driver name. And you can examine that in Etsy driver aliases. I want to caution you not to edit driver aliases by hand, but to use the utilities that we provide, add DRV, update DRV, and remove DRV, to modify driver aliases. There's also a file, name to major, that maps the name of the device driver to the major number. Devices have names, and so if you just take a look at the /dev, you'll notice a device that looks something like C0, T0, D0, S7. And that's its name. It's a link. That device name is linked to something in /devices, which has a longer name, which includes its device tree path. The next thing to pay attention to is the major and minor number. And the major number is just an index that associates with a device driver, and the minor number is an instance number. You can find the instance number. If you do a long listing of your specific device, you'll notice that just before date and time, there's a number, comma, another number. That is the device number, the major, comma, minor part. In this case, the major part is 86, the minor part is 255. The system also maintains a unique and persistent identifier, dev_T, to identify the device drive. Solaris has kernel APIs, and for device development, we have the device driver interface and the device kernel interface. You'll hear people describe it as DDI/DKI. This is an API that was designed to enhance the reliability and provide for stability in Solaris. It also provides, as a side effect, forward compatibility. The driver has been pretty stable for the last 10 or 15 years, and many drivers written for 2.6 or 2.8 will still run on Solaris 11. There's also a helper driver interface, GLD, the generic LAN driver. I'm not specifically going to talk about GLD today. It's currently version 3. It's a set of convenience functions and utilities. It sits on top of DDI, DKI, and it greatly simplifies developing a network device driver. So let's talk briefly about how to put together a simple device driver. There are some things that you need. The first thing you'll need is a set of kernel-specific header files. These are different than the user LAN header files. And I have an example here on the next slide or so. You also need to define some data structures. A data structure that is a pointer to the handle for this particular device. Some device configuration operations. How do you attach your device driver to a particular physical device? You need a structure that identifies the entry points that are the actual I/O operations for both character and block operations. And you need a way to load and unload. So there's a structure that points to the routines to load and unload your device driver. And, of course, the routines themselves. So, driver entry points. These are all described in the man pages in Section 9E. There's a loadable module interface that provides loading and unloading a device driver and initializing it. The entry points are init, fini, and info, and these are required for every device driver. There are some auto-configuration entry points, attach, and its cognate detach. Every driver must have an attach, detach, and a GetInfo. GetInfo returns the information about this specific instance. There's also probe and power. Probe is used for devices that are not self-identifying, and every driver should provide a power routine. This is a place where it enables all of the power on, power off functions so that you can hot plug devices, kind of an important feature. For character devices and block devices, you have an open and close. For character devices, you also have read and write. You can also map your device, and there are various I/O control utilities, IOCTLs, and a polling mechanism if your device doesn't use interrupts. For block devices, you have an asynchronous read, asynchronous write strategy, which is used by the kernel to actually position in the data. I'm not going to talk about, we don't have time today to get into how to memory map or talk about streams device drivers or system, but I will note here, dump, you'll notice in the structure is not filled out, but for a device that can be a core dump device, the dump routine must be specified. And of course, there's a quiesce routine to gracefully shut down a device. Just a note about kernel versus user device context. Most of what a device driver interfaces directly with the kernel and is called by the kernel, but there are some entry points that are callable by user programs, and this is pretty obvious. When you call open or close from a user program, it actually talks directly to the device driver. And of course, read, write, and IOCTLs can also be called by user programs. And so typically, those are going to be wait mode. So you make the call, you wait till it completes, and then the kernel returns control to your user program. Remember that the kernel is in the kernel address space, and so in your device driver, it's important not to attempt to access user space directly. There are utilities to facilitate that, DDI copy in and DDI copy out. Here's an example of the header files that you'll need for your device driver, and I've annotated them here so that you can tell what each of these header files means. In particular, you'll notice the last two, DDI.h and sunDDI.h. Those should appear in that order. Some of the other ones that are of interest, common error, and open and errno are all used, but there's a type def near the top. The first data structure that we want to talk about is a pointer to your device, and it's dip, and it's of type devinfo-t. I don't really need to talk much more about that. You can use this code directly. The next structure is the module operations, and I don't usually modify this either. This provides the utilities for loading and unloading your device driver. Now we're to the point where we begin to talk about the device operations themselves. So every device driver must have a GetInfo routine, and you'll notice this driver is XX. So you'll notice an XX underscore GetInfo. Just above that, there's a reference count. I'll just make a passing comment that this is initialized to 0. This is a reference count so that we can keep track of who's accessing the device driver and when it may be okay to detach it. Every routine must also have an attach and its cognate detach. I have not identify is no longer used, and neither is reset. The two left are probe for devices which are not self-identifying, and power, which will provide a mechanism for controlling power on, power off of a particular device. Here's the data structure for the character and block operations. Again, this provides the kernel with pointers from a general command to your specific device command. So the ones I've provided here are an open, XX underscore open, and I should have provided a close, but since open doesn't do anything in this very simple driver, I've left it null. Now I'll mention there's null dev and no dev. Null dev returns 0. No dev returns ENXIO. This routine simply presents open, read, and write. So now let's talk about the routines that are pointed to by those structures. Again, we have those functions that you're going to call from userland: open, read, write, GetInfo, attach, and detach. Or actually, GetInfo, attach, and detach are used by the kernel to instantiate this driver. The init routine. The only thing I'll mention about the init routine, this particular one doesn't do much, but whatever you do in your init routine, you must undo in your fini routine. There's also a routine that provides the information about this specific driver back to the kernel, and it's a pretty simple little routine. Now, the important stuff. Attach is how you actually attach a specific instance of this driver to a particular piece of hardware. There's a lot of things that can happen in the attach routine. Init and fini only get called once when you first initialize and when you clean up after the driver. But attach can get called for every instance, and it needs to be carefully crafted, and you may need to use mutexes or condition variables to protect sensitive data, since you can interrupt an attach routine by another instance of the attach routine. So you need to be careful about the state of the device. In this particular case, we're just allocating space for the software state of this device driver and its name, and not doing much else. Slide completes the attach routine. The one comment I'll make is you want to pay particular attention to your error routines and handle each possible error. Again, these device drivers live in the kernel, and not handling an error can have disastrous consequences. Again, the detach routine simply cleans up after the attach routine. So anything you do in the attach routine has to be undone in the detach routine. So let's talk about open for a second. Open can be called by the kernel, or it can be called by a userland program. In this case, I'm not doing anything. I'm just handling a couple of errors here. But you may have special initialization for an instance of a particular driver when you open it. Here's an example of read. Again, I'm not doing anything, but it gives you an idea of what a read routine would look like, even though it doesn't actually do anything. Here's a write, analogous, doesn't do much. Now, you can compile a device driver. I've provided the commands here for compiling and linking. Again, there's no main segment. You're just linking an object file that's going to be loaded into the kernel. Here's an example for Spark and x86 using the Studio compilers. It's also possible to use GCC, and I've provided the commands for linking and compiling here. Some device drivers will also need a driver.conf file, and they're named whatever the driver name is, .conf, and they live in the same directory where the driver lives. And it contains any properties that you might want to set. They're readable by the device driver. Frequently, you'll read this in the attach routine and set any particular specific properties peculiar to your device. Packaging. So up until Solaris 11, we used SVR4 packages. They still install on Solaris 11, but the native packaging system is IPS, and there was a webinar on IPS, and there'll be future webinars concerning IPS, so I won't talk much about IPS today. To install a driver, typically you do this in your package, but if you're developing a driver, you're going to install it by hand. You're going to copy your driver into an appropriate place. Your user kernel DRV is a place to put it. There's a new policy. People are putting local customizations for drivers in etc driver DRV, but it needs to be in a place that the kernel can find it. You can run the command add_DRV and my driver name. It'll ask you some questions about where the driver is located. I'll note that info, init, and attach are called in that order. The driver then gets added to the device's directory. And if you look at mod info, you'll notice that this driver will be the most recently added. And analogously, if you go look at etc named a major, it'll be the most recently added there, and you can get the major number. Drivers are loaded with the mod load and mod unload command. Typically, they're loaded and unloaded automatically when the kernel starts and it discovers a device that needs a particular driver. Testing. So when you're developing a device driver, I suggest you start very simply. Start with a skeleton device driver that doesn't do anything. Get it to compile and link, and you can load and unload. Test it to make sure that it doesn't have any memory leaks. There's a variety of tools you can use for that. Generally, you use a debugger like MDB. MDB and the : find leaks is useful for finding kernel memory leaks. That tends to be a typical problem. I usually write a little script that attaches and detaches the device a couple of thousand times. It's a good way to test to make sure that those routines cleanly do and undo their operations correctly and that you're not leaving a lot of garbage behind. When you're developing a device driver, make judicious use of common error. It's similar to printf, and scatter them throughout your code, and you probably want to use conditional compilation, if def debug around your error messages so that you can print them to the console and know exactly what's going on with your driver. You probably also want to set up an alternate boot environment so when inevitably you damage your bootable image, you can recover. You might also want to take a look at assert. It's pretty useful in a device driver to test for invalid assumptions and to force a panic so that you can then debug the exact state that occurred when something unforeseen occurred. It's particularly helpful when used with mutex_owned. Mutexes tend to be a difficult area in device drivers, and people frequently have trouble maintaining how they use condition variables in mutexes. So that's pretty much the material that I wanted to talk about. I went through it very quickly, but I do want to point out a couple of things. How you can get help. Of course, I'm going to suggest you join OPN. There's a free version. You need to be at the gold level in order to join the Solaris Developer Initiative, however. But for people who have products that they want to do device drivers for, this is the place to go. Of course, you can send me email. I'll do my best to answer your questions. If I can't, I'll find somebody who can. I want to talk briefly about some references. Of course, you can download Solaris 11. Here's a pointer to the Solaris 11 documentation. In particular, in that documentation, the Writing Device Drivers Manual has been recently significantly updated. It's very good. If you follow it, you'll have a pretty easy time writing a basic device driver. There's also a device driver tutorial, and pointed to here. It's also very handy to give you an overview of exactly what you need to do. Between these two documents, most of your questions should be answered. Writing device drivers goes into a lot of detail. There are example code segments in there that can help you with the more advanced topics. There are also the man sections for DDI and DKI driver entry points, the kernel functions, and the data structures. If you're developing for Spark and your hardware device needs to be bootable, I also suggest you take a look at writing Fcode, which is what OpenBoot uses. You can put this in the extended ROM firmware area on your device, and it'll allow that device to be discoverable by OpenBoot and can be used for boot. I might also point you to the PCI Special Interest Group. There you can find an index into the PCI vendor IDs and product IDs. So if, for example, you do a PRT conf and you find devices that are, but no device driver attached, you can find more information about what that device really is and the vendor. Here's a pointer to the DLPI spec if you're writing a network device driver, and the TPI spec. Both of those go together. A handy place to go look at source code and to get additional information. Open Solaris device driver community is still fairly active. There's a lot of people in the community there that, and a lot of legacy material there that can be very useful. You might take a look at that. And of course, you can also just Google Solaris device drivers, and you'll come up with a number of links of particular interest. I didn't create a link here on the slides, but there are a number of people who have either worked for Sun or Oracle and have familiarity with device drivers. You'll find pages for them. I'll turn it back over to Mike.
Yeah, thanks, Bill. Hang on, and we're going to go back to Bill for some questions. I did see a couple of questions slip by, though, about the slides, and this is the page where you can get the slides. Just download them. They're right on the registration page, as well as a recording of this talk Bill gave today will be up there in about a week as a replay, and you can see the previous webinars are all up there, so you can download the slides, you can listen to the replay. So keep note of those links, bookmark those links. What I want to do now is just briefly introduce the next two that are going to come up, as Bill mentioned, are around IPS. We had sent out a poll earlier in our webinar series and got a lot of feedback about more deep dive on IPS. I don't know if Eric's on. Eric, if you just want to say a word about those two, if you're on. If not, that's okay.
Yes. Can you hear me, Mike?
Yeah, perfect.
Okay, sure. Hi, everybody. This is Eric Reed. I've given one of these before, and as Mike said, when we polled people who took these webinars and asked, what would you like to hear from next as we add these to the end of our list going into the summer, what webinars would you like to hear? What came through loud and clear is we want more of a deep dive on IPS. IPS is new in Solaris 11. It affects all the packaging and patching, and people wanted to see specific examples, how to actually create and deploy packages, and what some of the more powerful and esoteric tools were. So the next webinar in 2 weeks will be on how to actually publish a package, create and publish a package. The one after that will be digging into the tools and GUIs and commands in some fairly deep detail. So I think anybody interested in packaging is going to want to tune in for those.
Excellent. Okay, why don't we turn it over? There were also some questions I saw floating by. Maybe we need to bring a few to the surface for Bill. And while we're doing that, I'm going to try and initiate a poll and see if we could get you answering a few questions for future sessions. But go ahead, let's open it up for questions for Bill.
Bill, this is Eric, and there were a couple that, as Mike said, were posted on chat, and one of them was, can you speak at all about compatibility of drivers that are developed in Solaris 11 and whether or not there are compatibility issues with other open Solaris base derivatives such as Nixenta, and whether those compatibility issues are known at all?
Well, yeah, I can speak to that. As far as I know, there hasn't been any divergence in the device driver interface, device kernel interface. So drivers written for Open Solaris or Solaris 11 should function well on Nexenta, SmartOS, and Open Indiana. The driver interface was specifically designed to be portable, not only between architectures, but carry forward to new releases. And as far as I know, no one has made any changes that are incompatible. So drivers written, as I said, even for 2.6, all the way forward to Solaris 11, those drivers, with a few exceptions and caveats, the binaries tend to continue to work.
Okay, there was a follow-up on that, which simply was a data point here. The chat person says, for instance, there is a kernel mode settings KMS for graphics drivers in Solaris 11 that doesn't yet exist in Illumos. So that's probably more of an FYI for people, but that's a possible difference.
Well, yeah, and I can mention a couple of other things. I mentioned the generic LAN driver, GLD. GLD v3 was not a published interface. It was not listed as a stable interface prior to Solaris 10 Update 7. Drivers written to GLD v3 prior to Solaris 10 Update 7, the driver interface actually changed in an incompatible way. It was still listed as a private interface, so I don't think we violated any rules. But if you use those private interfaces, your driver will probably need to be at least recompiled with the new header files after Solaris 10 Update 7. Otherwise, it will cause a kernel panic. That's one of the only big incompatibilities that I'm aware of. But it's just a recompile in most cases. You may want to take advantage of some new features in GLD v3, and those are being documented. Much of it's been documented now, but there'll be more documentation coming.
Here's another one. I assume, Bill, that you can't see the chat, so I'll just read the ones that I'm seeing on here, if that's okay.
Sure.
Question from another person. What does the devlinks, DEVLINKS, command do?
Okay. It's been a while, so I'll have to get back to you.
Yeah, we can certainly do that. For any questions we don't answer today, we are making note of the chat here, and we will get answers for the questions that we're not able to answer right here. Here's another one. Is there a document that points out differences between Solaris 10 and Solaris 11 for kernel driver development?
The best thing to do, or the easiest thing to do, other than the man pages, is to compare the two writing device drivers manuals. I mentioned GLD v3 has changed a little bit. There are some new functions and features in GLD v3. I'm trying to think of what else. The basics of the device driver have all remained fairly stable. Of interest to the graphics, since there was a graphics question, a lot of graphics drivers are really layered. So you may be aware that the XSun Windows Server was deprecated, and we began using Xorg. So device drivers need to have a slightly different interface to Xorg. So some graphics drivers will need to be modified. That's another possible change. Is there another question?
There was a follow, let's see. How would you suggest debugging device drivers, graphics drivers, and others from a user perspective, e.g., how to best report driver bugs, etc.?
Well, that's a little tough. But typically when a driver fails, of course, they can fail in a number of different ways. There are, of course, functional changes that can occur. So a driver might not be functioning correctly, but still not do any harm to the system. Most drivers should behave pretty well in the sense that they don't panic or hang the system. When drivers, when you write past an array end or something like that, you step on some other part of the kernel's code, and usually that results in a hang or a panic, and you'll need MDB to figure that out. I'd have to think about, if there are specifics about the kinds of errors you're looking for. One of my peers is actually better qualified to talk about graphics drivers than I am. I've actually never written a graphics driver.
Okay. I don't see any others in chat that I didn't cover, but as I mentioned before, those that we either didn't see or weren't able to cover just in this presentation, we'll be researching offline, and we'll be augmenting the FAQ, the frequently asked questions, for this developer series.
But unless there's other questions for Bill, I think we'll call it a wrap. Bill, excellent. Thanks very much.
My pleasure. Thank you, everyone, for attending.
Thanks.